Hello. So in the last few videos, we discussed simple harmonic oscillators and harmonic motion, focusing on primarily the example of a mass on a spring and of the simple pendulum. Now what we're going to do, we're moving on to the next sort of topic to end out our semester. And this is the idea of waves. And the sort of goal in the first chapter is to learn the basic properties of waves and how to describe them. And then in a second chapter on waves, we'll look at effects like interference and different things of that nature. So we have to start with what is a wave, right? And our general definition of what a wave is going to be some sort of disturbance traveling through a medium, right? So we have, if you think about probably the most common example of a wave, we have just a water wave where, say, you have some flat pond, you drop in a stone rather into the water. That disturbs the surface of the water, right? You can think of the water is the medium the wave's traveling through, and sort of the height of the surface of the water is disturbed. You get some swell and some trough here, and that disturbance, the shape sort of that surface, travels through the water at a constant speed. That is sort of a general way to describe a wave, whether it's a water wave, an electromagnetic wave like light, or any of those things. You have some medium, and there is some sort of disturbance or displacement of something in it, and that disturbance travels through the medium. Now, there are essentially two types of waves that we can categorize them into two types of waves. The first is a transverse wave, like the water wave we just looked at. Transverse wave is when the displacement or that disturbance of the medium is perpendicular to the direction which the wave travels. So the most obvious sort of standard one of this form is if you were to grab a string or a rope and give it a little flick, you would disturb that rope, the medium, up or down, but that disturbance, that wave, would travel along the rope. So you have a disturbance up and down, and the wave traveling left to right. And those are perpendicular. We would call that a transverse wave. The other type is a longitudinal wave, where the displacement or the disturbance in the medium is in the same direction as the wave travels. This is what happens with sound, um, and a lot of other types of waves. But essentially, one example is if you take a spring or a slinky and hold it stretched and just smack the end a bit, you'll see that the spring compresses a bit and goes back and forth this way, and that disturbance travels along the wave that way. And we can watch a brief video showing sort of how these look.
You can see here we've got a transverse wave where the slinky's displaced up and down, but the disturbance travels left to right again. And in the longitudinal wave, you give it a kick along the slinky, and you can see this sort of compressed part of the slinky that's disturbed, traveling back and forth along that slinky.
Now, one of the things that can help us when we start to think about trying to develop quantitative models and all that of how to describe waves is, again, how to visualize them. And there's essentially two different um, types of graphs or plots of waves that we like to use. The first one is what we call a snapshot graph, right? And it gets its name from a snapshot, like taking a picture of things. So if you imagine a wave traveling along a string, like in this case where we have the triangular wave traveling along the string, if you were to just take a picture of that string at that instant, you would for 1 second, 1 instant in time, have that displacement, that delta y of the string at all positions, right? So this is what we call a snapshot graph, and it's because you're essentially looking at 1 instant in time, but plotting all the displacements as a function of x, right? Um, the You can make sort of motion diagram type images out of this, or use them to help visualize how that wave travels by essentially taking a snapshot graph at a given t1. You get the shape of that string or the displacement as a function of position, and then successively take additional snapshot plots And you can see that that pulse or that disturbance is traveling along the string at each successive snapshot. And the distance that that pulse sort of travels is just the speed of the wave speed times the delta t between those images. And the wave moves at a constant speed. That's what we're gonna. That's going to be a property of all the waves we look at, is that the wave's traveling at a constant speed through the medium. Um, the other type of plot that we can have, that we look at, is what we call a history graph, right? And this is where you can look at the displacement of a single position in the medium and plot the displacement as a function of time. One of the interesting things about this is the leading edge of the wave is actually on the left-hand side of this plot because it happens at an earlier time. So the shape of the wave, this wave was traveling to the right, the shape of it actually flips when we go from a snapshot to a history plot, because the earlier time is on the left on the snapshot plot. And you can sort of see how this works if we compare the two. So if we look at that sort of the successive snapshot graphs we had previously, we see, you know, this sort of this triangular type pulse moving to the right. The leading edge is the steeper edge. It's coming, and it, you know, as the wave comes this way, it's the leading edge. It hits it first. But if we want to plot, make a history plot and look at position x1, the first thing that it sees is that leading edge. So as we increase time, all of a sudden that wave gets to that location and it starts to go up that steep edge first. So that's why we have this sort of reversal of the shape when we have a wave traveling to the right in position, and when we go to a history plot, those switch. We can also plot these types of graphs for longitudinal waves. It's a little harder to see because, you know, you're not taking a picture of it. But if we were to imagine that slinky type longitudinal wave, where before the wave's there, we have just evenly spaced, you know, rings on the slinky. But then as you know, compressed or smacked the end of that slinky, you've created a disturbance where those slinky rings or those points on that slinky have moved left or right, and they're displaced some amount. And then that sort of compressed region, that disturbance, travels through the wave at a constant speed. But you can plot those individual disturbances on a vertical axis. It's going to be the delta x disturbance. And as you can sort of see here, for what would be this t1 equals 0 seconds sort of snapshot graph, we have equilibrium points, and then this one's displaced to the right a bit, so it would have a positive displacement. 2's displaced a certain amount. Then you can make that plot. It's just not as obvious to see it as say that transverse wave, because you're actually looking at the displacement, and the snapshot graph looks like that displacement. Up until now, we've been describing essentially single pulses, right? We look at this, we give it a little flick, that disturbance travels to the right. But you know, we want to start thinking about, just like we did for simple harmonic motion, we started thinking about oscillators and then sort of looked at a specific type, the harmonic oscillator. What we're going to do now is, rather than describing these arbitrary single pulses and that, we're going to look at what happens if we have a continuous regular disturbance. So rather than, say, dropping one stone into a pond or something, we continuously, you know, bounce up and down, you know, you just put your hand on the water and bounce it up and down slightly and continually disturb that. If we think about what that wave would look like, well, we would essentially get these sinusoidal waves if we were disturbing that medium with a sinusoidal or a harmonic oscillator type disturbance. You can imagine holding the end of a string and just going up and down with your hand like a sinusoidally, or with a simple harmonic oscillatory type motion. You're going to just continually create those pulses, and you're going to end up seeing that wave travel through the string and form a sinusoidal type history graph. If you look at a snapshot graph, if you look at the history graph, you get the similar type shape as well. That's sinusoidal in time as well. And that is, excuse me, this sinusoidal wave are extremely important or useful in describing all types of waves. There's some mathematical theories or principles called Fourier analysis where you can create essentially any type of periodic function or pulse by adding up a bunch of different sinusoidal waves. So if we can get really good and efficient at describing these individual sinusoidal waves, mapping that to a general wave shouldn't be that big of a leap. So we're going to focus on these sinusoidal type waves. Looking at sinusoidal waves, we can define a few things that are going to make it much easier for us to describe them mathematically. If we look at this snapshot graph of a sinusoidal wave, we can see we have this sinusoidal type disturbance along as a function of x along our medium, and we can see there is going to be some amplitude of that disturbance. It's sort of the maximum displacement of the medium from its sort of equilibrium position, right? So that amplitude, sort of the same way we used it with our harmonic motion type description of harmonic oscillators. We also have, the wave speed. It just describes how fast that wave is moving through the medium. But the big new one is the wavelength, which many of you are probably have heard before or familiar with it. Probably think of it as the distance between two neighboring crests or two neighboring troughs, or essentially it is just the distance in space it takes for this sinusoidal wave to repeat itself, right? If I go from here all the way to here, I am back at an equivalent position to where I started, or equivalent displacement to where I started. We define that as one wavelength. Now, that's not as quantitative as a definition as we want for wavelength. The way I prefer and the way the book describes it specifically is we can think of the wavelength as the distance spanned by one cycle of motion, right? And to see how that works, let's just do some, those motion diagram type snapshot graphs of this sinusoidal wave. So if you look at one instance in time, we have a snapshot graph of that sine wave. And then as time progresses, that moves to the right at the wave speed, and it keeps going, it keeps going, and it keeps going. And after one cycle of motion, as in the time it takes for the position here to go down and then back up to where it started, that time is one period of motion for that piece of the medium. The crest has moved a certain distance we call lambda, the wavelength, in that period of time. So the wavelength is defined as the distance traveled during one cycle of motion. Is a very useful way to think about it because it allows us to sort of relate some of these properties. The wave speed is sort of the big thing it does. We can use that sort of definition of wavelength to come up with sort of a fundamental relationship for the waves we're going to look at. The way we do that is, well, we know that speed is distance over time. And if we've defined the wavelength, lambda, as the distance traveled in one cycle of motion, and the period is the time for one cycle of motion, we get this relationship where the wave speed is just that distance, lambda, over the time, the period. But if we think back to how our period related to our frequency of motion with simple harmonic oscillators and these periodic motions, we can write this wave speed in terms of frequency of the wave. And we get this sort of fundamental relationship for the waves we're going to look at, where the wave speed is equal to the wavelength times the frequency. And that's a really useful, we're going to see this a lot, and we're going to use it a lot when we get into our quantitative descriptions of these waves. So let's do that now. Let's look at our waves, what we know, and try to develop a quantitative model of it. So if we think about a wave, it's a disturbance in some medium that travels through that medium. So we're going to need to describe some quantitative model that's going to describe that disturbance, and it's going to have to be a function of position and time, right? It's going to depend on where we are in the medium, is going to inform us of how far that medium is displaced or not, and at what instant in time. So we need to develop some mathematical description of that disturbance as a function of position and time. And we know that since we try describing these sinusoidal type waves, that it's essentially going to be a sinusoidal function, right? Now, just to try and keep this, not generally arbitrary, but a pretty simple description that involves both those variables is some constant times position and some constant times time plus just some constant again, right? So let's look at this model. Turns out, I'm putting the cart before the horse, and this is what it's going to be. But let's look at this description for the displacement and start to think about why this works, right? So what do we know? Well, we know that if I were to make, some snapshot graph of this sine-like wave, that at some position x naught, my displacement, my d at x naught, at some given time, we'll just set it at t equals 0, is going to be the exact same as my displacement at x naught plus one wavelength, right? If I move one wavelength to the right here, I'm at the exact same displacement, d x naught plus lambda at t equals 0. So I can look at that and say, okay, my displacement at x naught at t equals 0 must be equal to my displacement at x naught plus lambda times t equals at t equals 0. So just plugging in these numbers into these equations, well, with this model, I would have a sine k x naught minus omega t plus phi naught. This, has to be equal to the same function but evaluated at x naught plus lambda minus omega t plus phi naught. Now, I set t equal to 0 here, so just to make things easier, let's plug that in and set that equal to 0. The point is, this wave description gives us x k naught plus times x naught, plus phi naught. It has to be equal to a sine of k x naught plus k lambda plus phi naught, right? And if we're familiar with sine functions, right, we know that if I take a sine function and I shift it by some amount, the only way that that can be equal to the same amount is, if we plot sine like this, just sine of x as a function of x, this is pi radians, this is 2 pi radians. We know this is periodic in 2 pi, right? It's going to repeat itself. No matter where I am, if I go 2 pi radians to the right or left, it's going to be the same. The only way this equation is going to be true, which we know it has to be because of our, how we describe waves and our sort of definition of a wavelength, is if k times lambda, this extra term here, is equal to some multiple of 2 pi, right? Or k is equal to 2 pi over lambda, right? And this is actually our definition of what we call the wave number or the wave vector if we're in multiple dimensions. And what it essentially does is it has in it the periodicity in space of our wave, right? It depends on this wavelength. And what it's doing is it's converting essentially any location in position into radians, right? This has units of radians per meter, or just inverse meter. So if I plug in any position here, this k sort of converts it to radians, so it's an acceptable argument to a sine function, and it's periodic in 2 pi. So I know if I move one wavelength to the left or right or in position, I end up with the same value, that same displacement. So that's our first sort of definition here. Wave number k is 2 pi radians over the wavelength lambda. It describes our periodicity in space in our wave function. So what else can we look at here? Well, let's look at how waves move, right? So if I have this sinusoidal wave, snapshot of it, displacement as a function of time, it looks like this. It's moving to the right with some wave speed v, which means at some later time, it's going to look something like this. The exact same thing, just moved to the right. So this is my displacement as a function of position and time. And we'll say this one's my displacement as a function of position at t equals 0. Now, what's the difference between these two plots? Well, this displacement as a function of position at some time t naught is just the displacement at t equals 0 shifted by some amount vt, right? Or to write that mathematically, what that's saying is my displacement as a function of position at some time t naught is equal to my displacement as a function of position minus vt, so just shift that function to the right by vt at t equals 0. Those two kind of have to be equal by just knowing how that wave moves. So what does that mean? Well, I can plug in this sine kx minus omega t plus phi naught, sort of our wave model, but we're at t equals 0, so this term goes to 0. This is a sine k. Our x value is actually x minus vt plus phi naught, right? So this is what, if we just think about how this wave moves, this must be true. The wave at some time t is the wave at t equals 0 just shifted to the right by how far it's moved. So expanding this out, we get sine of kx minus kvt plus phi naught. This is just a way of writing our wave function as a function of t. There's nothing special about t naught. Let's just call it t in general. And we have this. Now we can think about what we just went over with when we were looking at our wave number, and that the wave number kind of captures the periodicity in space of 2 pi over lambda, and we can substitute that in there. And we also have sort of our general equation for wave speed, which was the wavelength divided by the period, the distance traveled in one cycle of motion, which can also be written as lambda times f. So this was, one of our fundamental sort of equations that we've come to today, where the wave speed is lambda, the wavelength, times the frequency of that wave. If we plug those in there, we end up with our displacement as a function of position and time is equal to a sine kx minus, well, this is 2 pi over lambda, and then the wave speed is lambda times frequency, and all that times t plus that constant term. Well, we see some things cancel here. The wavelengths cancel, and we're left with a sine kx minus 2 pi times the frequency times time plus phi naught. Now, this should look really familiar to you. If you recall looking at simple harmonic motion or uniform circular motion, we had that our angular frequency or angular velocity, omega, was equal to 2 pi f. That's the same thing we have here. This angular velocity of our wave is 2 pi f. So we can finally rewrite what we have here as kx minus omega times t plus phi naught gives us our displacement as a function of position and time, which is our wave model, where we've defined a few things here. We have angular frequency, which is the same sort of definition we've had when we've run it into before, 2 pi times the regular frequency. We have angular, or sorry, not angular, we have wave number, k, which is 2 pi over lambda. And this all comes together nicely in our sort of wave model that we're going to use to describe all waves. A few things. The wave number, k, again, this is 2 pi over lambda. It sort of captures the periodicity in space of our wave, and the fact that if we plot it, it repeats itself. It's periodic every wavelength if we plot that displacement as a function of position, right? The angular frequency or the angular velocity, 2 pi over f, we can rewrite that as 2 pi over the period, right? It captures the periodicity in time. If we were to plot a history graph, the displacement as a function of time, it's also going to look sinusoidal, but it's going to repeat itself once every period. One cycle of motion gives us that the period that it repeats itself. Basically, what they're doing is, I like to think of the wave number converts a position, this x value, into radians so that it matches the periodicity that we're trying to describe, and we can now plug it into the argument of a sine, and it makes sense because this would have to be, a unitless or in terms of radians, whereas the angular frequency converts this time into radians and in a way that matches the periodicity in time. Anyway, I think this is essentially where we're going to stop today. We will do definitely a lot more of this in the synchronous sessions and get used to it, how to apply this equation and how to use it when we're describing waves. Much like when we were looking at our simple harmonic motion problems, a lot of it is just getting used to how to translate the thing we're trying to describe into the language that we use in here, into what's the wave number, what's the angular frequency, what's this, what we would call the phase constant here. Once we get sort of comfortable with that, I think we're in a good place for how to describe waves in a quantitative way.